First of all, thank you very much for coming to our Lunch and Learn. My name's Matt Nowell. I'm the EBSD Product Manager here at EDAX. And what I'd like to talk to you today about is a product we call OIM Analysis. And so the title is What's New, what it can do, and how you can improve your materials characterization. When I put this together, this is sort of the list of goals I kind of want to hope to communicate, is that introduce EBSD and where OIM Analysis fits in the EBSD picture, some of the what I call basic analysis outputs that are available with the product, then some of the more comprehensive analysis options that are included. You're going to see through the scope of the talk that there's a lot of different things we can extract from the software. Try to give you some feel for what we can learn from this type of information for different characterization problems. Some of the things we put in the software to make it easier to use both as users and microscopists. And I make that differentiation because oftentimes people using the microscope are collecting data for people who have sent in the samples, and there can be a little bit of a divergence into what different groups want to accomplish. And then finally, I'll wrap things up with what's new in our latest version, version 8 of the software. So for those of you who are not familiar, EBSD, or electron backscatter diffraction, is an SEM-based characterization technique. We take a sample, we polish it really well, we tilt it to about 70 degrees, we hit it with the electron beam. When that beam hits a grain, it creates a diffraction pattern that's detected with a low-light CCD camera detection system. And it makes a pretty, you can't actually see the laser on the screen, but it makes a pretty arrangement of diffraction lines on the pattern. So generally what we do is something that we've called orientation imaging microscopy, or OIM, which is essentially automated EBSD mapping. So we couple our computer to the SEM and the camera. We specify an area of interest, both in terms of an area, but also a sampling size. So we might say we want to look at 100 by 100 micron area with a 1 micron step size. That defines our total analysis collection. At each point we get a diffraction pattern on the left. We analyze it through image processing to find the position of those lines in the pattern. Those lines correspond to different planes in the material. That tells us what the crystal orientation is on the right. And we do that for every pixel in the acquisition area. Why is this important? It comes down to anisotropy. Materials will have different properties in different directions. So the graph I've shown many times is the idea of wood in a weak orientation or a strong orientation. If you're going to try to break a piece of wood with your hand, it's in good interest to your hand to orient it in the weak direction. If you orient it in a different direction, you have a lot more higher probability of breaking your bones, probably. This same thing occurs on a crystallographic level in a material. You can have some orientations that are strong, some orientations that are weak, and the properties can be different. Sometimes it's going to be thermal expansion or acoustic propagation speeds. But if you're able to measure these orientations, it's the first step in being able to control and engineer properties based on this anisotropy. And so if you're like me, when you first learned all this, is that the thing you were taught is, well, anisotropy, don't worry about it. It all averages out. We might put a safety factor in and it all comes out in the wash. But generally, most ways of forming materials does introduce some level of preferred orientation. That's just an energetics effect or a slip effect. And so EBSD is really a great technique to be able to understand anisotropy on a next level and start to think about how to take advantage of it. And so OIM really falls in this place of how do we understand the relationship between microstructure, materials processing, and materials properties. And so OIM Analysis is the tool that's going to give us a lot of the different metrics to characterize the microstructure that we look at with EBSD. When you come to a show like this and you learn about EBSD, a lot of times the focus is on the acquisition system itself. How fast is the camera? How fast does it go in and out? Is it vacuum sealed? Whatever. Collecting the data is really the first step. The next step is in trying to analyze this data and understand it. And so OIM Analysis is the toolbox that provides the different types of analysis to look at different aspects of the microstructure, which I'll try to explain. And so you'll see these different types. The most popular, most common thing you see are these orientation or OIM maps. First thing is they're very colorful. They're pretty. We love to put them up. You'll see they're all around our booth and superimposed on different things. Not only are they pretty though, they can provide meaningful information. And we're able to color these in different ways as we can apply a grayscale option, so black to white coloring. We can apply colors, or we can superimpose them on top of each other to add different contrasts. And so, as in all imaging, contrast is information, and we're able to assign different contrasts to different information in the microstructure. At the same time, we can numerically describe the data, and this is just examples of grain size or grain boundary character distribution or grain shape. When you're able to get numbers and standard deviations and distributions, it's a lot easier to compare quantitatively different microstructures. And then at the same time, we can look at the distribution of misorientations. We can see if there's a preferred misorientation, a preferred grain boundary type. We can quantify the amount of preferred orientation. We do that through what we call plots. Now, to make this a little easier to use, we've put in what we call a QuickGen or quick generation toolbar. And so this is kind of the starting point for the software to access the most common maps, charts, and plots. One of the things that I'll emphasize a little later is you can customize this, you can grow off of this and expand on it, but it gives access to the most common thing. The most common map you'll see for EBSD, I think, is the orientation map or IPF map. In this map, the points are shaded according to the crystal orientation. And so by that I mean, in this map, if it's colored red, it's close to a 001 orientation. This is a steel cubic sample. If it's blue, it's close to a 111 orientation. And so very quickly here, we can see there are areas that are solid color. We can see there are areas that are sort of a shimmering color. Solid is where it's a single orientation. Shimmering is where the orientation varies a little bit. It tells us it's deformed. And we can see different sizes and shapes of grains that are present from that orientation map. So we get a lot of information quickly from a glimpse of this map. I like to emphasize that this map tells us a lot because we're seeing spatially resolved orientation measurements. This is an example I like to show. This was an extrusion that had different mechanical properties that they couldn't quite examine, and they looked at it with X-ray diffraction, they looked at it TEM, and they were saying, as far as we can tell, the grain size is the same, the texture's the same, everything we can measure is the same. Then we looked at it with EBSD, and as you can see easily, they're very different in terms of the spatial distribution of the red and blue orientation components. So they've clustered together much differently, and it's hard to resolve this clustering without this spatially specific information. X-ray diffraction would average that together. They would appear the same, but clearly they're very different. So these orientation maps can give you a lot of information at a quick glance. The next button would be the image quality map. This is a map that just, it looks like grain structure. It looks a very high contrast grain structure, especially compared to the polished surface we use for EBSD. This looks very comparable to what you might get from a nicely etched micrograph. But in here, the contrast we see is grain boundary, strain, plastic strain contrast that pops out at you. The next map is what we call our grain map. Here rather than coloring by orientation, we randomly color the grains to show size and morphology. But when we do this, we're also able to include or exclude different types of boundaries. So in this case, this is a solar cell. The twin boundaries of the material have different electrical properties than random high angle boundaries. So when we think about grain size, if we ignore twin boundaries, we'll get a different grain structure on the right than we would if we include them. And so when we think about recombination effects, this grain size on the right more fully describes how it will behave as a solar cell than the grain structure on the left. And that leads into the idea of the grain boundary map, is that we can color the different grain boundaries according to misorientation, according to special misorientation. So this is just a default one where we see a lot of high angle boundaries and some twin boundaries. You can adjust the colors. But EBSD is really the ideal tool for measuring grain boundary character distribution. We can measure lots of grains, and we measure lots of grains, we measure lots of grain boundaries. So compare that to a TEM when we're looking at usually 1 or 2 or 3 boundaries. Here we get a large number of statistics as part of the acquisition. And then if you have a multi-phase sample, we can also see the phase distribution. We can identify different phases, see how they're spatially located. This is an interesting one where you get a phase that rings around other phases in a geological sample. And with our system, we can also simultaneously collect chemical information, elemental information, with the EBSD acquisition. So you can see here, this is a material where we can see magnesium, silicon, iron, and calcium. We can blend these EDS information, and we can use that chemical information to correlate with the crystallographic characterization. We can show pole figures and inverse pole figures. We can see these are not randomly distributed. There's kind of a donut-shaped clustering in the bottom right that tells us if there's a preferred orientation present. We can get grain size distributions out. We can get average grain size numbers. And that's really important. You know, I like to put this quote up, is that, you know, grain size is often the major parameter used to describe polycrystalline performance. And so here's a Hall-Petch strength equation. Here's one for strain rate equation. So being able to quickly pull out that grain size information helps correlate to models of performance. And at the same time, we're able to use EBSD to answer the question of what is a grain. You know, it's a tricky question when you start to think about deforming material, but when we use this discretely measured orientation information, we're able to set what we call a grain tolerance angle. So here you see we've set it at 10 degrees, 1 degree, and a half a degree, and then in those center images we've randomly colored the detected grains. As we decrease the tolerance angle, we see the subgrains within the microstructure get better defined. And so when you look at a material, you may not think of, well, what grain boundary tolerance defines a grain. This gives you a tool to help investigate that, so you can say, for whatever property I'm interested in, this would probably be the most appropriate description relative to the different grain boundaries. And we can quickly see the misorientation distributions. And again, these distributions can really strongly affect how your material behaves in something like corrosion or creep or fatigue. As I mentioned earlier, we can take these images and we can create a grayscale image, we can create a color image, we can combine them together, and you can customize this. So you can really communicate the picture you want to see to describe the problem. So this is some deformation that occurred from a shock wave in a meteorite. And so we're trying to see the structure on the left with the orientations in the middle to kind of create a composite picture. The reason I emphasize that is that when we start getting to the point of customization, in the software we have what we call templates. So if you've gone and you've set up something, so here we've said image quality and color scale and these boundaries, once you've decided what you want to show, you can save this and then repeat it easily for either one map or a set of maps or a whole analysis. That really makes it easy to share and collaborate with users to a facility, different universities or whatever. You can define an analysis and replicate it at the push of a button. That's important because there's lots of types of analysis. I've walked through the basics, but there's advanced analysis of grain size, shape, and properties. There's advanced boundary analysis, so this is looking at grain boundaries, twin boundaries, intergrain misorientations and reconstructed boundaries, plane traces. There's advanced material properties, so this is an example where this is a little peg of tantalum, and the idea is if you compress it, what shape should it be? And what happens is, because this material deforms, it slips on a certain slip system, we're able to better predict how it deforms. It deforms differently than you would expect based on how the crystallography is distributed along that material. And so we can look at this in terms of that type of deformation, elastic modulus, dislocation density measurements. And then we can take these distributions and we can determine how strong or how multiple times of a random distributions are at in what we call texture analysis. And we can take all this data and we can manipulate it, we can rotate it. And so one of the things I wanted to show is the idea of, here's a very large area. You can see it's sort of a centimeter-ish scale bar, a large area of a friction stir weld. And we see in the middle what's called the weld nugget. On the edges we see the base metal. And you can look through there are these different rings of material. And it's called sort of this onion ring structure. And so what tools can analyze that sort of thing? Well, we can go into the software, we can go in and crop out different sections of those onion rings, pull them out as different sections, and look at the orientation distributions for those different regions to see basically the friction stir weld. They have a pin that stirs through the material. you can see how the material kind of fans out following that pin direction as a functional location. Once we have these measurements, we can correlate it to different types of processing material. So this is just an example. This is rolling of brass where it's rolled 5, 10, 30, 10, 20, 30. I'm forgetting one of the 4, obviously. But we roll it more and more, and we can track the amount of plastic deformation, the amount of dislocations that are introduced in the material as we deform it, how the grain size changes, how the grain shape changes, which grains deform more or less, so that as we want to optimize our rolling, we can see exactly what happens in the microstructure to give very quick feedback into that process development effort. This is an example I like. This is indenting a sample and thinking of what sort of factors microstructurally can affect the indentation response. So I took an indenter and I indented it into 3 different materials. So the one on the left is a nickel superalloy. It had 14 micron grains. We indent it. The indent width is about 150 microns. You can see in that image, the blue area is a stress, strain, low deformation area. As the colors warm up, we see the deformation that's induced by the indenter. Okay, so we'll use that as sort of a baseline. We go to Inconel 718 where the grains are smaller. Okay, if you think about your microstructure, smaller grains means stronger material. So we do the same indent. Obviously my arrows are a little distorted from where they should be, but it's not quite as wide, 150 to 135 microns. That strength makes that a little bit less responsive to the indent. Then I went to a stainless steel with very small grains and lots of twin boundaries. A lot more strain was initially present. That's why the colors are warmer there, and the indent doesn't go as wide. So we're able to look and say, what things can we measure? We can see how that response correlates to the response in a mechanical indentation. And this is another kind of cool example. This is a titanium clip, and it's actually used to close an artery in pediatric surgery. So my son had one of these implanted when he was just about a week old, and the doctor gave me one. I said, I'd love to look at that under the microscope. And so the straight area up above is sort of the normal area, and then there's a bend area at the left. And it's the idea of what can we see in there. So if we look at that bend area, we see an orientation map from the bend area on the top and then the base area on the bottom. And if we look at the orientation spread map on the top right, you can see where it's bent, we get compressive and tensile strain that's implied, and it introduces plastic strain into those areas. And obviously you don't want it to break, so you can measure how much goes in there, how close it gets to failure in terms of the amount of plastic strain introduced. And this is just an example of a partially recrystallized steel where you're able to go in and not only do we see the orientations on the left, but we can see on the right areas that are recrystallized versus deformed to get an idea of fraction of both as a function of heat treating. So we can extract lots of parameters that correlate to different processing variables. With that comes lots of data. So that's the unfortunate side effect of having lots of options. But what we've introduced is what we call our project tree that helps organize all this data in sort of an intuitive manner. So you can see in this project, there can be multiple data sets, there can be multiple sets of data within there, different maps or plots or charts on different levels. And within that you can cut and paste and you can save the whole project. It's easy to take all this data and put it in a meaningful perspective for organization. One thing we're able to do, and I touched on it with this, is this idea of partitioning. Sometimes when we look at a microstructure, it's not a homogeneous microstructure, and you may want to extract certain parts for analysis. So in this example, taking that partially recrystallized steel, we may want to measure the recrystallized area versus the deformed area and say, well, what's the grain size and what's the plastic strain level for both of those different components to get a relative strength of those. And so we can define these, we can save these definitions as a template, apply them, and combine them to get, I want large grains, highly deformed with only this much chemical composition to build large partition logic to really identify the microstructural feature of interest. And once you have this data, we can also go and interrogate it manually. You know, that's obviously a little more time consuming, but in this example, this is a stress corrosion crack in a stainless steel piece of pipe. You see the crack on the orientation map in the left. Going in and clicking across the crack propagation path, we can pull out what are the grain boundary types that are cracking. So the microstructure itself, the overall misorientation distribution is shown in that red distribution on the right. So there's lots of low angle boundaries, that's deformation, it's a worked piece of pipe. And there are lots of boundaries near 60 degrees. Those are the twins that are present in the stainless steel. Well, if we look at the crack, it's going across boundaries that don't really match up with either of those. It's going around more random high angle boundaries. So there's an effort for this type of material to do what's called grain boundary engineering, where they do different thermomechanical processing to put more of those 60-degree boundaries to make it more crack resistant. When we do interactive analysis, you can do point-to-point misorientations, you can do point-to-origin, we can see what the unit cell and different planes are. Once you've done all that, you can export it and save it, you have it available. The other thing you're able to do is highlight data. So I can go to a certain distribution. In this case, I've selected everything. I apply a color scheme to that. I then show that color scheme on the map. So in this case, I'm looking at grain size. I now see where the small blue grains are relative to the large red grains, and kind of understand the relationship between different measurements that we make. This is from an in situ experiment. So it's deformed material. At certain points, we want to make some measurements. So we end up with a large number of data sets. How do we analyze these efficiently? So we've created what we call a batch processor. So in this case, this is just showing as a function of temperature, different data sets. So what we're able to do is come in here and say, what do we want to do for each data set? And for in situ measurements or 3D measurements, we can do auto alignments, we can do auto crops to take out any local measurements or whatever. We can do any cleanups we need to do, and then we can apply a template to extract different repeatable maps at each step, so we get the same map at each point, and all these can then be saved for subsequent analysis. So if you're doing a set of experiments, you can repeat them over and over again to create your outputs. Again, we clearly recognize there's lots of data. It's very easy to get lots of data. So we also put in tools for, we've called this the OIM data miner, but it helps to organize the data. So what you're able to do is run this, it sort of indexes your hard drive and says, here are all the data sets that are on a drive, on a portable drive, on a server drive, wherever you want to do. It shows you what phases are present, the number of points, the step size, the confidence index, the elements, and you can open and delete and find duplicates, and all from this tool here. And it's just a way of helping to organize the large amount of data that's possible with the technique. And when we talk about large data, of course, we can also start to do what we'd call 3D EBSD and even 3D EDS, where we take multiple data sets, but in between each one we remove a layer of material. And sometimes that can be done mechanically, sometimes that's done with a focused ion beam or a plasma fib, to be able to get spatially resolved data through a volume of interest. And so once we've done that, we're able to take this data and create 3D volumes of information. But when we do this, the thing that's unique is we're able to analyze it as a function of orientation. So just like I showed finding grains in 2D by looking at misorientations, we can extend that to 3 dimensions and see grain structure and relationships. This is a meteor right there on the left, and it forms very distinct planes based on the cooling rate of the meteorite. So we're able to extract things out about orientations, phase, elemental distributions, and local orientation variants. We can get grain size, grain shape, average orientation. We can go in and pick out specific grains with transparency levels and see here's what a grain shade, a grain facet looks like in 3 dimensions. That leads to what's new in version 8. So the first thing that I'm happy about is that it's multi-threaded. What that means is now when you buy a fancy new computer, we're taking full advantage of that. So your performance basically scales with the amount of money you want to spend on your computer, which wasn't the case, obviously. We're also able to do what we call pattern indexing in the analysis software. And the reason that's nice is we're no longer tied directly to the microscope. You can get all your data, take it onto your laptop, and then do whatever you want on it. So we can index either using the Huff peak information, that's the band location we find on the microscope, or we can actually save all the patterns and reprocess them offline. We can re-index either a single point by partition or the complete data set, and it allows us to do what we call chi-scan and NPAR, and I'll explain both of those. It also enables batch reindexing. So if you have done 3D work or in-situ work, we can reanalyze a batch of data sets much easier. This is just a little slide showing when we bring in a pattern, we can come and adjust the phases, we can adjust the band detection, we can adjust the calibration, we can optimize image processing directly for whatever pattern we're looking at. So if you've had a sample and you say, hey, I found a phase I didn't expect, it wasn't indexing well, you're able to come in and say, now I can index that much easier because you have direct access to all the information and all the parameters to analyze it. Chi-scan is using EDS with EBSD to improve your phase differentiation. If you think about polymorphs in material, you can have in iron, you can have austenite and ferrite that EDS has difficulty differentiating. They're both essentially iron. Structurally with EBSD we have the same problem. We can have copper and we can have nickel that are both face-centered cubic and very similar lattice parameters. The diffraction patterns look about the same. And so what we're able to do is by using both EDS and EBSD, we can differentiate the phases reliably. So this is an aluminum silicon casting alloy. The phase map on the left is obviously very noisy. That's not correct. The phase map on the right, when using the chi-scan approach, now we see the aluminum in red, the silicon in blue. We see the phases correctly. Once we have the phases correctly, then we can do all the subsequent analysis with confidence. NPAR is something relatively new for us. This is an approach we use to improve the signal-to-noise ratio in the pattern by locally averaging patterns that we collect. The important thing for us on this chart, the vertical axis there is indexing success rate. We obviously want that to be high. The horizontal axis is noise level. So as we put more noise into the patterns, our conventional indexing distribution in red there drops down. That's not good. But when we apply the NPAR approach, it brings it back up. What does that mean? It means we can collect data faster at lower beam currents. And it's good for things like insulating materials or beam sensitive materials. This approach allows us to still get good performance without having to sacrifice on the collection. So this is just an example. This is without NPAR, 11% success, very speckled. Generally when you see speckling in EBSD maps, it's bad. On the right, it jumps up to about 96%. This is just one of a slide from a systematic study, just to give you an idea of what we mean by noisy pattern. So if you look at the top left one, that's our quote unquote good pattern. It's already pretty noisy. We're starting at the poorest areas. You squint there further at the bottom, like the pattern D, you're going to have a hard time convincing yourself there's data there. But we run that through the NPAR processing, you see we're getting the exact same microstructural information. So we're pretty happy with that. So that lets us go to things like, we can go 100 patterns per second at 100 picoamps. Generally, we're going to run somewhere more around 10 nanoamps, so we're 2 orders of magnitude lower in terms of beam current and still maintaining, relatively high speeds. And this is 500 points per second at 500 picoamps. And again, still significant improvement in performance. Another thing we do is what we call PRIAS. PRIAS is a microstructural imaging approach where we're looking at orientation contrast. We're now able to do this fully in OIM analysis. When we do this is some of the information we get. We get topographical contrast on the left, orientation contrast in the center, atomic number contrast on the right. And all this sort of happens in the background automatically. So what that leads us to do, this is an example from a thermal barrier coating in a nickel superalloy. This better shows, I think, you see the phase contrast on the left, grain contrast in the center, topographic contrast on the right. So we get these multiple contrast modes that are all collected as part of the EBSD acquisition. So now we're able to do this basically on every sample we look at, we get these different contrasts. And you can see this just array, 4 different samples, 3 different detectors, lots of new information, lots of new contrast that's available. But in the analysis software, what we're able to do is to try to isolate this a little bit better. So this is that same set of 3 images, and what you see is orientation contrast coupled with topographical contrast. So what we want to do is to say, can we minimize the topographical contrast and enhance the orientation contrast. So we take our patterns, we define a thin vertical region of interest and create the image using that area. Then we get only orientation contrast, we suppress the topographical contrast. So we get more flexibility in defining how we create these images to get the contrast mechanisms we're interested in. And this PRIAS also is useful for in-situ stuff at higher temperatures where forward scatter detectors don't work so well. This is just an example going through phase transformations near 1000 C in a material. The PRIAS images there that's on the right on the section of all three still give very high contrast, high information density imaging. We've also put in some stuff for correlative microscopy. This is just important because one, when we're looking at the tilted sample, our EDS and EBSD interaction volumes don't overlap, so sometimes we have to shift those. But we're also able to correct for when we go to a flat sample, different techniques. We can bring those all into the sample to correlate additional analytical techniques with the EBSD microstructure, because we're always looking for correlations to explain what we see. And we can do the same thing with correlative plots. In this case, we've picked dislocation density on the horizontal axis, Taylor factor on the vertical axis, to understand how do these different measurements relate to one another. And we can do what we call anti-grain analysis. There are points that we can't analyze with EBSD, they don't give diffraction patterns. We can still group those together and look at things like size and shape. So in this case, this is looking at porosity in a solar cell. Porosity is bad, it's a non-absorbing area. So we're able to measure porosity, size, and shape, and area fraction is a function of thermal processing to say how do I minimize my pore fraction while at the same time getting my texture, grain boundary, grain size information. HDF5 support. Again, we get large amounts of data, large amounts of say patterns. This is a standard file format container that allows for enhanced portability and correlation with things like cross-chord analysis for HR EBSD, Dream 3D for 3D analysis. OIM analysis is applied to everything. So automotive alloys, fatigue in aerospace, trilobite eyes is one you probably don't expect. I've talked about solar cells, nuclear materials. It's used basically in all crystallographic material. There's a lot to it. So I like to mention we have lots of different ways to help learn how to do this. So manuals, tutorials, videos, courses, web sessions, webinars. If you really like this one, you'll probably be able to watch it again in a week or two. We know there's a lot to it. So we try to provide a wide range of materials to help learn and help it grow with you as you're learning. And finally, if you're interested in more, there's an introduction to the whole technique and also a bulletin on the new OIM analysis features that's available over at the desk there. So with that, I'll stop and just summarize that it's really a comprehensive but hopefully easy to use toolbox for characterizing our EBSD data. The new pattern indexing brings new capability in optimizing your data, and multi-threading allows us to use modern computers to their fullest extent. So with that, I'll stop. Do we do questions now, or I'll answer questions, then we have some more speakers. So.